Morning everyone. Today myself Dhairesh Shrivastava and Arush Goyal as well as Ayush Kumar are going to present you on about Superscalar CPU execution simulator. Our project objective is basically to build a simulation environment which visually shows how superscalar processors execute multiple instructions in parallel. Instead of learning theory, we wanted to see cycle by cycle execution on screen. Our core purpose is to simulate instruction level parallelism. Modern CPUs don't run one instructions at a time, they run many instructions simultaneously. Our simulator models how the CPU pipeline handles the instructions in parallel and how out of order execution actually works in hardware. Technical focus is basically on core architectural blocks, reservation stations, reorder buffer, as well as multiple execution units. These are actual elements that make parallel execution possible. Our system models all these components so that we can observe how instruction issue, execute, and commit. Project motivations. Our project motivation is out of order execution and dynamic scheduling are very hard to imagine just by reading theory. On paper, we see block diagrams, but we never learn how to instructions actually move inside the CPU pipeline in real time. Because of that, students get confused about how data hazards, resource conflicts, and dependency handling works. So our motivation was to build a simulator that makes everything visible so we can actually watch how instructions issue, execute, and commit. This makes the theory of superscalar architecture much more practical and easier to understand. Our project scope is basically divided into four parts. First, we take assembly language input and convert it into internal presentation. Second, we support basic operations like arithmetic instructions like load, store, and branch. Third, we simulate the core hardware architecture. This includes reservation stations, a reorder buffer, and multiple execution units so that parallel execution is possible. And fourth, we generate detailed cycle by cycle output logs, which show exactly what happens with every instruction at each stage.
Project Progress. We have successfully built the core engine that progresses the clock cycle and updates all the processor components. Instruction fetch and decode are operational, and the system can read the assembly input, pass instructions, and queue them correctly. Reservation stations and the integer ALU are integrated and capable of issuing and executing arithmetic instructions, and operands are ready. Finally, we designed the robust data structure for the order buffer, register file, and reservation stations. Challenges we encountered: data hazard logic. Designing the common data bus to correctly broadcast execution results for all waiting reservation stations proved exceptionally complex. Reorder buffer management. Maintaining in-order commit schematics while allowing out-of-the-order execution requires sophisticated state management algorithms to track instruction completion status. State synchronization. Keeping registers, reservation stations, and reorder buffer states consistent across each clock cycle proved particularly difficult to debug due to stable timing dependencies. Next steps and work remaining. Moving forward, we will add a branch instruction system support along with a basic branch predictor and a pipeline flush mechanism. A dedicated load store unit will be introduced to correctly handle memory dependencies and hazards. We also plan to build a comprehensive test site to validate correctness across all hazard scenarios. Finally, we'll aim to improve the simulation output by creating a cleaner, more initiative pipeline visualization for students and developers.
For developing a superscalar CPU simulator, we chose Python 3 because it supports fast prototyping and clean object-oriented design. We used VS Code as our primary IDE since it provides debugging tools and easy version control for team collaboration. Our implementation relies mainly on Python's built-in data structures like lists and dictionaries to model key hardware components such as reservation stations and reorder debuffer. This environment allowed us to build and test our architecture efficiently. In a demonstration, we'll run a small assembly program that includes load, arithmetic, and branch instructions. The simulator will show the pipeline activity cycle by cycle, highlighting how instructions issue, execute, and commit. You will clearly see out of order execution where independent instructions finish earlier and how the reorder buffer maintains correct program order. Finally, we will also show a branch misprediction scenario and how the pipeline flushes and recovers. Our project is nearing completion and the core execution engine is already working. Going forward, our focus is on completing branch prediction logic, implementing the memory access unit, and performing rigorous testing to handle edge cases and hazards. After that, we will polish the user interface and finalize documentation. Our target is to finish the complete simulation system by the end of this month and ensure it works accurately across different instruction patterns.